This here video contains the solution for 2006 AP Physics C Mechanics number 2. We have a nonlinear spring compressed to various distances x, and the force required to compress it is measured for each distance. Data are shown in the table. And we're assuming that the magnitude of the force applied by the spring is of the form F equals ax squared. Now remember that Hooke's law is F equals kx or negative kx if you're paying attention to direction, which they're not here. So this is not obeying Hooke's law. So that means everything that we know that comes from Hooke's law does not apply. Okay, so we have to be careful later on about that. That's what they mean when they say that this is a non-linear spring. A linear spring would be kx, as in no exponent. So kx is like a straight line. So which quantities should be graphed in order to yield a straight line? Well, if we want to do like y equals ax, then I think we need to make this x squared, whose slope could be used to calculate a numerical value. And if we do graph that against that, or sorry, force versus that, the slope actually will be a. So it should be easy enough. So the answer to part A is you should graph. Remember we graph y versus x. So we're going to graph x squared versus f of x. So x squared versus force. So part B, calculate values for any of the quantities identified in A that are not given in the data, and record these values in the table above. Label the top column, including units. Oh, thanks for reminding me, AP Central. Alright, so let's go ahead and square our x's. You see that? Okay, so 0.05 squared, 0.0025, 0.1 squared, 0.010, two significant figures. 0.15 squared is 0.022 or 23. 0.2 squared is 0.0, I knew that. And 0.25 squared is 0.0625. Ha ha ha, without a calculator. Okay, so now let's graph those. They want us to actually graph them, so if you get confused, remember this y equals ax, so the force should be over here, force in newtons, and on this axis we should have x squared, that would be units, would be meters squared. And let's see, our forces go from 4 up to 106, and I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and a little bit more. So if I go by tens, I should be able to get the 106 up there. Let's make that 10, 20, 30, 40, 60, 80, 100. You get the idea. And here, let's see, I'm going from, if we looked at this decimal place, if this, you thought about this as being like 2, 10, 23, 40, and 62. So I'm going up to about 62. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Let's make this 0.06. And this would be 0.05, 0.04, 0.03, 0.02, 0.01. That looks good. Alright, so 0.02, that's like, this would be 0.005, and then 0.0025 is halfway there. And that corresponds to a force of 4 newtons, so somewhere around there. 0.01 goes with 17. 0.023 goes with 38. 0.04 goes with 68, looking pretty linear, and 0.0625 goes with 106. So that looks pretty pretty dang linear. You could put it in your calculator, find the line of best fit, however you like to do that. Let's just do that quickly. Stat, edit, list 1, clear list 2, and our x values are 0.0025, 0.01, 0.023, 0.040. You want to do this kind of thing as fast as you can, because your time will be better spent elsewhere. 38, 68, 106. Stat calculate line of best fit. It looks like the slope is 1701, and there's a tiny y-intercept, which we would expect. Use the graph to calculate A. So my answer for part D is 1,700. Let's say 1,700. And what is that slope? What would the units be? Well, it's kind of like a spring constant, but it's actually slope, so it's newtons per meter squared. Nonlinear spring. So there's your answer for part D. The spring is then placed horizontally on the floor. One end of the spring is fixed to a wall. A cart of mass 0.5 kilograms moves on the floor with negligible friction and collides head-on with the free end of the spring, compressing at a maximum distance of 0.10 meters. All right, we're going to find the work done by the cart in compressing it and the speed of the cart before it strikes the spring. All right, let's see if we can do that. Let's do that on a separate sheet here. So what we need to remember here is if this were a linear spring that obeyed Hooke's law, then the potential energy stored up in it would be 1/2 kx squared, and this would be very easy. We could just use this. But it's a nonlinear spring, so I can't use this. So we got to remember, where does this come from? Well, remember, potential energies are the antiderivatives of the forces that are associated with them. And that might may put you in mind of the fact that this is the antiderivative of the kx, right? So in this situation, if the force is equal to ax squared, then the integral of a force with respect to x is equal to the energy associated with that, or more specifically work, and that equation is given to you. There should be a dx there. So the integral of the force gives us the amount of work done. So let's see if we can find that integral. So the integral of ax squared dx is equal to a over 3 times x cubed. And oh yeah, we know what a is, don't we? It's 1,700. So, and how far was it compressed? It got compressed 10 centimeters, or 1/10 of a meter. So that means that the work done is 1,700 over 3 times 0.1 cubed. So 1,700 over 3 times 0.1 to the third, and it gives me 0.57 joules of work. And then the speed of the cart, I think here we can say that conservation of energy, this is a spring, so if that's how much energy the spring stored up, that's the amount of energy that the cart must have had. So the potential energy held by the spring must be equal to the initial kinetic energy. So that gives me 0.57 joules, must have been equal to 1/2 was the mass of the cart was half a kilo times its velocity before it hits the spring squared. So let's see, that's a half times a half, so multiplying that over to the other side, however you like to do that, it's 4 times 0.57, and then we want to take the square root of that, and that's not what I wanted to do. I wanted to take the square root of 2.28, which is about 1.5 meters per second. Not too bad.